Hello, ESC 101. We are going to go through the first part of the plate tectonics lecture. And what this part will focus on is how the theory of continental drift came to be. It primarily started with Alfred Wegener. And this guy, he was a scientist in the early 1900s. And as you can see here, that he had a lot of jobs. The primary thing that he did was working with climate, meteorology, but he also is kind of described as a geologist, geophysicist. He didn't have any formal geology education, which you'll see plays a role later, but he is given credit. He's the originator of the continental drift hypothesis, which was published in 1912. So what is this hypothesis? Well, Wegener proposed that there was this supercontinent, and he called it Pangaea, which is Greek for meaning all Earth. And what he proposed was that all the continents were a part of a supercontinent, and they moved to their present position. Okay, so let's take a look at some of the evidence that he found to support this hypothesis. One of the first things we'll cover here is evidence in the rocks. You would have these mountain ranges. You have the Appalachian mountain range, which is over here, and mountains that go up through eastern Greenland into Europe. As you can see, they even go up into Scandinavia. And what was found was that the same rock types, geologic structures, and ages that are in the Appalachian Mountains was also in these mountains in Greenland. And the only way that this could possibly occur when you're on either side of the ocean is that at one time when those sediments were being deposited and those structures being formed, they must have been together. Okay. Another bit of evidence for continental drift was looking at fossil evidence. Now, fossils themselves can be used to relatively date rock layers. This was something that we mentioned way in the beginning of the semester, but as a rock layer or a sediment layer is being deposited, animals that die, their hard skeletal parts or even sometimes soft tissue is preserved as a fossil. And then that fossil can help date other rock layers relatively, meaning that it's before or after when this fossil, this organism, lived. Well, what supported continental drift was you would have these organisms, such as this seed fern, was across several continents. And this seed fern did not have the ability to spread naturally to these continents in their present location. Two other fossils that help support this was there was this Mesosaurus. It did have swimming ability, but it was very limited. It couldn't swim across, say, the Atlantic Ocean from South America to Africa, etc. Same with these two terrestrial reptiles. Think of it as like a box turtle or one of our snakes, an iguana. These things can't cross oceans either, but there is a lot of fossil evidence in all these different continents. And so this also supported the notion that the continents were actually together at one time. Some other evidence looked at deposits from glaciers. And glaciers are huge masses of ice and snow, very heavy. And besides acting like a plow, pushing fragments of rock, depositing sediments, you also have that ice scraping against the rock and dragging huge chunks of rock across the rock beds. And that's going to leave striations and marks in these rock layers, which is structural evidence. And also the location of this glacial deposit is often in places where it's too close to the equator and you wouldn't get glaciers to form in the beginning. So an explanation for that would be that the continents were together closer to one of the poles, in this case probably the southern pole, and glaciers could form and would leave their deposits in grooves. So climate kind of dictated that glaciers couldn't form in that equatorial region. It's too hot. Well, in this case, it's climate again, but enabling the habitat of coral reefs. And they're a tropical thing primarily, and these were found in bits of the continents that would be associated with near the equator. But these regions aren't close enough to the equator now, and also the same type of animals that make the coral, other animals and plants that would live in that coral reef, fossils of those are found across this widespread area. And if you take that fossil evidence, the evidence of coral reefs, and line those up, you would start to see that the continents kind of piece together again like a jigsaw. So let's take a look at the movement of the continents and kind of reverse them from where they are today and back to what possibly could have been a supercontinent. Okay, so you have the movement of the plates. Remember, this is kind of in reverse here. And as these continents kind of move closer together, you start to see a little better of how present continents can fit together almost like a jigsaw puzzle. I remember as a kid looking at a globe before I even learned any of this stuff and kind of noticed, especially right here, boy, that looks like I would fit together. You might have too. So once that the globe was mapped pretty well, these kind of spatial awareness concepts started making scientists think. And Wigner was one of the first ones to propose this. Now, with this evidence, you would think that, well, that's pretty convincing, and that scientists, geologists would have jumped all over it, explaining the natural phenomenon. All this evidence trying to explain a story that would encompass all of it. However, his hypothesis was unaccepted at the time, fought pretty heavily in some circles. So let's see why maybe this was unaccepted. Well, one of the main things that people debated that this couldn't possibly be was, how could these continents move? They're massive, right? Solid rock. How could they be moving and slamming into each other? What force could do that? Well, Alfred worked on this and tried to come up with several things. One was, of course, we had an understanding that the Earth is rotating on an axis. And if you've ever had like a piece of string with something at the end and spun it around, okay, that's centrifugal force. And that force is in an outward pattern. And it would push these continents away, kind of break up Pangea and move those continents. Well, he called that pole fleeing force to try to give a mechanism to this continental drift idea, to show what drove the movement of the continents and supply that evidence. But it was, the whole thing about science is that scientists peer review the stuff and they're trying to disprove it, right? Well, somebody took that, worked the math, and concluded that that force is insufficient to move these continents. It's not like a sailboat on a lake being pushed. A lot more mass to move. Then Alfred came up with, well, you have these gravitational forces of the sun and the moon, and that's what creates our tides. It creates this ocean bulge and affects the tides coming in and out. Part of it. It's part of the reason. And that too was laughed at, just not enough force to move this stuff, rejected. And at the time, Earth was thought to be solid. We know now that you have these different layers of the Earth. You have that inner and outer core, a mantle, which is kind of plasticky, okay, not liquid per se, able to move and change shape, very hot. And then you had the crust, that thin layer on the outside. Well, they didn't know that at the time. And, like geologist Franz here, quite frankly said, there's just not enough force for one continent to plow through the crust in the ocean to move. So as I mentioned before, the continental drift hypothesis, it was proposed in 1912. Fought very hard, mainly because of the lack of a good mechanism driving the movement of plate tectonics. Well, as more knowledge was attained, and understanding that our Earth is not just a solid rock, and there are these intense radioactive reactions occurring in the core, creating an immense amount of heat. Well, that heat needs to dissipate, and something hot rises, something cold will sink. Well, in areas in which this heat dissipation is focused, you have this upwelling of hot material, and then as it begins to cool, it's pushed to the side as more hot material is coming up. Okay, let me get my pointer going. You have upwelling. That material cools, gets pushed to the side, and as it cools, it begins to sink again to be reheated and continue that cycle. That's a convection current. Well, if these convection currents have a strong localized area, such as the Mid-Atlantic Ridge, this could possibly be a driving force of moving these plates. And it's due to that dissipated radioactive heat. Okay? And then this kind of built off of also some other concepts about seafloor spreading. There's evidence that there seems to be areas, that Mid-Atlantic Ridge in the ocean, that the crust appeared to be moving away from a central location. And it began to be put together that that upwelling of hot material could be pushing that material away. So you had there in 1929 the advancement of possibly a mechanism for driving plate tectonics. Still not quite enough to fully change the thoughts of other scientists, other geologists around the world. Well, after 1929, little history, you're building global tensions. World War II breaks out. Well, during times of war, you have immense technological advancements. You had submarines. Submarines had to navigate. They're trying to map the sea floor. They're using different types of equipment to find enemy submarines, etc. Well, besides some discoveries during the war, things that they would sense using their equipment, in the 50s, after the war, and that equipment's just laying around, the public, the scientists then get their hands on it and start applying it to their work. And, magnetometers was a piece of equipment. It was invented a while ago, but was being used often during this time. And they started to really work on understanding the magnetic field of the Earth. Now, that's a whole another lecture on why or how the Earth forms this magnetic field. Has something to possibly do with the differential of composition of the layers of the Earth and the spinning and all this stuff. They're still working on that. But they were able to measure it and map this magnetic field, its intensity, its direction, and they began to apply it to rocks. And what they discovered was that magnetite, a mineral that you learned where a magnet would stick to it, right? Well, an igneous rock, when that mineral was crystallizing, those crystals, okay, when it's molten and it's beginning to crystallize, would align with Earth's magnetic field at the time that rock is formed. So they line up, which created this record of where the poles were. We created this map of Earth's magnetic field. And what they call the magnetic polarity, that is the direction of this field. You have that North Pole, South Pole, and that line from pole to pole would be called that magnetic polarity. And they began to map this in the oceans. They started applying it to terrestrial rocks, anywhere where this magnetite or similar minerals that would align in this field. They began to gather this global evidence. So let's take a look at continental evidence. Well, what they were able to determine was that in fresh volcanic rocks point to the current magnetic North Pole, which is what we just discussed. But as they would apply it to older rocks, they too would point to a magnetic north, but it was different than the one we have today. And as they began to map all the rock types and aging them, they began to see that rocks of different ages don't point to the same locations or the current magnetic pole. Something's up. You got rocks pointing in different directions. So as you're developing this global map of rocks of various ages, pointing in different directions, got to try to explain this. And using critical thinking, you could come up with 3 scenarios. that could explain this. What are they? Well, the first would be that the continent stayed in the same place, but magnetic north moved. So as the North Pole moved and new rocks are formed, they're going to point to that pole. And then the North Pole moved again. And then new rocks point to that. Okay, that's possible. Another one, opposite. The pole stood still, but the continents are moving. Continents move, igneous rocks are formed, points to the North Pole. Another explanation. Then there's the third one. Both the continents and the North Pole moved. Okay, possible as well. Well, as they continued to look at the evidence, lots of calculations, models, etc., what they determined was it's kind of a little bit of both, but primarily continental drift. Those continents are moving, and as new rocks are formed, they're pointing to the magnetic north. And what they called that is apparent polar wandering. Okay, apparent polar wandering. So you have a little bit of the pole apparently seems to be moving around for this rock evidence, but it was actually because the continents were moving, and the new rock would then point to where the North Pole is. So this concept of the Earth's magnetic field and mapping it over geologic time isn't something new. This concept, this field of study, is called paleomagnetism. And one of the earliest mentionings of this was from a United States submarine. And that as they're sounding the Earth's floor, the ocean's floor, and their instruments are able to pick up, the magnetic orientation of the rocks, it seemed to be alternating. The poles themselves would also reverse. So the North Pole would actually change to be the South Pole. And this was very evident in the Mid-Atlantic Ridge, to where you had these bands of changing magnetic polarity. And Bernard here, he started documenting this and publishing research in 1906 about this banding that's occurring. And this was out there, but yet, didn't fully understand it, didn't have global evidence to really fully support continental drift. But it did kind of pave the way for seafloor spreading, a mechanism to be driving continental drift. So the seeds were sown, but we needed more information, more knowledge, more technology to get a grip on this. Well, besides that, why did it take so long for global scientific support, the geologists, to support this concept? Well, let's take a look at that. Well, there was problems with the hypothesis, right? You had a lack of understanding of that driving force, that mechanism of plate tectonics. You had evidence that kind of pointed to, yeah, this happened, but we need to know how. Is it possible that this happened? So that was a lack. And that whole concept of paleomagnetism at the time was very unappreciated because we didn't fully understand it. We didn't have lots of data, global data, that could support this global geologic process. Well, also that fossil evidence, the rock type evidence, and coral reefs, all that stuff That data is being collected, but it takes time to scientifically analyze it in a way that is sound. And you have to interpret the data. What does this data mean? And that takes time and knowledge building. So you had this going on. And again, the whole global aspect of this data collection, we're not looking at a process that only affects, say, California. We're looking at the globe. And you think of, today, it's a little, we're very global, very global. Things can be shipped from China in days to us. Now, well, just sending a letter from one continent to the other could take a month, let alone data collected, published, shared, analyzed, things like that. So you had this lack of data and sharing of knowledge. There was this time delay. And there was also alternate explanations for the paleomagnetism, the common beliefs at the time. If you remember, a scientific theory is the best explanation of some natural phenomenon that we can come up with the evidence and knowledge and technology we have right now. So you had these explanations that people commonly and widely accepted. And you have to dethrone those. That takes lots of time as well. And the other thing is, once you get a train of thought in science, and think about it, in everyday life, you have somebody that I know that this is true, whatever it is. Most people resist change. It's hard to accept change. People have to accept being wrong. Not an easy thing to do. And so that also delayed the change in the geologic arena to support continental drift. And besides paleomagnetism, to explain these other groups of evidence, there was other theories that were accepted in some circles. Something in geology, you had kind of two major powers, so to speak, two prominent trains of thought or groups. You had European group and you had the United States. And, they kind of conflict each other and there's this competition between each other, who's better. And, oftentimes there is this resistance to accept what another group has come up with when they have their own ideas. Again, that played a role. And another thing that I've read is that Alfred Wegener's credentials, he's more of a meteorologist. He's trying to explain geologic processes that are, rocking the world. It's totally could revolutionize geology. This guy doesn't have any formal training. He never got a college degree in geology. He didn't get a PhD in it. And he's arguing with people that have PhDs in geology. So you can see, again, resistance there. It's like a mechanic is working on a car and has been trained to work on cars, has been doing it for decades, and then here comes this guy who, say is a bricklayer, and he is saying, well, you're wrong. This is what's wrong with the car. That mechanic's going to resist that train of thought, isn't he? Well, kind of the same thing's occurring. Well, this guy doesn't know what he's talking about. He's never even been to school for geology. You can see how that can work. Some people, they never grow out of that either, do they? Well, what support finally turned the tides and completely made continental drift a scientific theory and the widely accepted explanation of this geologic process today. Well, you had lots of advancements in understanding paleomagnetism. We have started to understand it better, mapping where it is, patterns that were occurring. We also started to understand seafloor spreading near plate boundaries, especially in the mid-Atlantic, that ridge. Uh, lots of submarines out there, increased technology to map the seafloor, revolutionized geology. That it, every resource that I've read greatly attributes this mapping procedure post World War II of the oceans. You think about it, that's a pretty good military advantage to know what's out there in the ocean. There's mountains under the ocean. You don't want your sub running into it. You want places to hide from enemies, and where could the enemies hide, etc. Well, that kind of bled into the scientific world and help us understand more about seafloor spreading, that World War II tech. Also, in general, you had this huge advancement in technology. Think about it, getting close to the space race time. Computers were invented and starting to be used to analyze and process an immense amount of data that we're collecting. And not only in geology, paleontology, fossils, seismology, okay, seismic waves, like earthquake stuff, or how sound moves through solid or liquid materials. We'll touch on that when we cover earthquakes and ocean. So you build up all this support. Well, when people write about history, you have a perspective, and oftentimes you add a little drama. Well, Alfred died in 1930. His concepts, his hypothesis wasn't widely accepted, you know, 60s. I have a textbook, physical geology textbook, that was written in the late 50s, and it was still describing plate tectonics as a hypothesis. Well, with all those advances and everything, finally it does. Well, when writing about it, they kind of just made Alfred to be this lone genius that was uh, made fun of and ostracized and victimized, blah blah blah. Well, that's kind of a mischaracterization of what happened. And in reality, the European Geologic Union, they were accepting lots of this idea as early as the 20s. Okay, especially as seafloor spreading started to be more understood. USA took a lot longer. A lot of that seafloor spreading stuff was being done by Europeans, so they had quicker access to it. Could talk to the guy quickly. He worked down the hall type of thing. But it was being accepted. And once it was accepted, this blows my mind. Now, with today's technology, using GPS, in real time, we can measure not only how fast continents are moving, those plates are moving, but their direction. Where are they going? In this image here that you see, this is showing each color is a different technology uh, or system. That's a better way of putting it. Different systems that are in place to measure the movement of the tectonic plates. And as you see, they are very similar, the different systems, and it just blows my mind that we can model this, where things are going. And from my understanding, the length of the arrow, this would be a vector. And not only is it showing the direction, the longer the arrow, the faster, say, per year, these plates are moving. Some of them are centimeters a year, which doesn't seem like much, but in geologic time, that's pretty fast. So that is an ultra Cliff Notes version of the evolution of the continental drift theory and the scientific process that occurred for it to be widely accepted. Okay, this is a science class, and the processes of science, the application of the scientific method is important. So this section, even though it's not really explaining how plate tectonics work, it will be important for you to understand the timeline and the types of evidence that supported continental drift. And this ends part 1. I will start to work on part 2.